Welcome to the Chapter 12 of the Oil and Gas Engineering audiobook. This chapter presents the work and the deliverables of the electrical discipline. The electrical discipline is in charge of sizing, specifying, selecting all the plant electrical power generation and distribution equipment. It is also in charge of producing all documents which are necessary at site to install this electrical generation and distribution equipment. The starting point of the electrical engineer is to draw the electrical consumers list. It consists of making an exhaustive inventory of all plant electric power consumers. These include obvious process consumers such as pumps, as well as some hidden consumers such as this lube oil heater inside a compressor package. Not all consumers operate at the same time. Therefore, to estimate the overall plant power consumption, one must take into account the type of operation, whether it is continuous or intermittent. This is done by identifying in the electrical consumers list the type of duty. Is it continuous, intermittent, or spare? A spare equipment, for instance, operates only when another one is not operating. The overall power consumption is then calculated by summing the consumed load times what is called a coincidence factor, which will be 1 for continuous consumers, maybe 0.5 or 0.6 for intermittent consumers, and 0.1 for spare consumers. Indeed, for spare consumers, it is still required to consider some power being consumed when this consumer is started while the other one is not yet stopped. Electrical discipline coordinates closely with process to identify which are the most demanding process operating scenarios in terms of electrical power consumption. Let's consider, for instance, the case of this compressor station. It has 6 compressors in a 4+2 configuration. This means 4 compressors are running, 1 is spare in hot standby, and 1 is available for long-term maintenance. Now, what shall be the power consumption considered for the compressors, the maximum power consumption? It is not 6 times the consumption of one compressor. It is neither 4 times the consumption of one compressor. Indeed, when one compressor has to be taken out of service for maintenance, then to ensure that the plant duty is still met, operations need to put a 5th compressor online before the compressor is taken out for maintenance. Therefore, at this point of time, 5 compressors will be running. So 5 times the consumption of one compressor is the maximum power consumption of the plant. This allows to size the plant power generators. As uninterrupted power is required, there are several generators in order to have backup. If one fails, the other generators can compensate and take up the load. For instance, if the total power consumption of the plant is 4 megawatt, 3 generators, each of 4 megawatt capacity, would be a suitable selection, such as the one that has been made here, 2 generators will operate at 50% capacity and one would be spare. If one generator fails, the other one that is already running will be able to cover and go to 100% and take all the load of the plant. Once the capacity of the generators has been defined, the generators can be ordered. The next step of the work of the electrical engineer is to define the power distribution. The electrical power supply to power consumers, such as pumps, is done at a low voltage. This is an industry standard and the voltage is 400 or 600 volts. This means that the power supply cable carries a high current and therefore has a high cross-section. The same power, if carried at a higher voltage, would require a cable with a much smaller cross-section, as the current would be much lower, and the cable cross-section is determined by the current. This is the reason why transformers are used, so that electrical power is only carried by large cross-section expensive cables at low voltage over a short distance, and electric power is carried by medium voltage cables like 10 kV cables over a long distance. Therefore, electrical substations with transformers are located throughout the plant. Let's see how this is done. Large power consumers are identified on the plot plan. For instance, here, the large power consumers are the air-cooled heat exchangers. Electrical substations are located next to these high power consumers, so that the length of the low voltage cables is minimized. This distribution is shown on the electrical single line diagram. The electrical single line diagram shows all the electrical equipment and their geographic location. It includes the power generators, which produce power in medium voltage, so they are connected with a medium voltage switchgear, typically 10 kV. Then the transformers from 10 kV to 400 volts, and then the low voltage switchgears or motor control centers. And the electrical substations are also shown on the single line diagram. Once this electrical system has been set, it is subject to calculations. The load flow analysis performs the calculation of the voltage and current in every part of the system, as well as short circuit calculations. It allows to identify the maximum current that each equipment must be able to sustain, hence to define the rating of this equipment. Once this is done, equipment datasheet of all the equipment can be issued. This datasheet, such as the one shown here for the transformer, not only shows the capacity and the rating of the equipment, but also some preference regarding the technology. For instance, if the transformer shall be a dry type rather than oil-filled transformer to have an easier maintenance, and so on. To order a switchboard, it is necessary to specify what type and quantity of incomers and outgoers are to be part of the switchboard. In addition, the types of protections, i.e. circuit breakers, to be provided for each incomer and outgoer must be specified together with their rating. The types of protections is specific to each type of consumer. For instance, an electric motor will not require the same type of protections as an electric heater. Controls must also be defined. For instance, for a motor, control signals from the process control system to start or stop the motor, as well as signals from the process safety system to shut down the motor in an emergency. These signals exchanged between the process control system and emergency shutdown system with the MCC are shown on switchboard typical diagrams. The plant power generators are fueled with gas from the process. In case of process upset or shutdown, the fuel gas to the power generators is stopped and the generators shut down. Some consumers need backup power. These are, for instance, the auxiliaries for rotating machineries, which must remain operating after the machinery is shut down to cool it down. Another example is fire water pumps. These consumers are called essential consumers. They are provided backup power supply from emergency generators. Emergency generators are diesel fueled, hence they are not dependent on fuel gas from the process. The essential consumers are identified by electrical on the consumers list. The identification of essential consumers is done by the electrical engineer by asking process and mechanical engineers. A load shading system is implemented so that in case of loss of the main power generators, in case of loss of normal power, the limited amount of essential power available from the emergency generators is fed to the essential consumers only. This load shedding, together with other functions of monitoring and control of the electrical system, are performed in the electrical control system, also called the Power Distribution Control System, PDCS. Now that we have seen the various pieces of electrical equipment, let's look at the drawings that are produced to install all these equipment at site. The electrical equipment layout drawing shows the arrangement of the electrical switchboards in the electrical substations. Electrical cable ways are wide. Indeed, electrical cables, contrary to instrument cables, must be separated with a separation distance allowing the heat to dissipate from the power cable. Therefore, the cable trenches occupy a large footprint. Therefore, the electrical cable routing has an impact on the plant layout, and the electrical main cable routing must be produced early by the electrical engineer so that these routes, cable trenches, this allocation of the required space is taken into account by the plant layout engineer. The cable schedule, together with the cable routing drawing, will allow to install the cables at site. Typical installation drawings will be issued, such as the one shown here for a local motor control station. Similarly to the instrumentation loop diagram, which show all information related to one instrument, the electrical troubleshooting diagram shows all information related to each consumer, including reference of the switchboard and cubicle, numbering of terminals and tags of cables, connections with other systems such as the process control system and emergency shutdown system. Therefore, this drawing is used for troubleshooting. If there is any issue with this particular power consumer, then this drawing shows all where to check. Besides the calculations we have already mentioned of the electrical system, the electrical engineer performs cable cross-section calculations as well as transient analysis, the loss of one of the main power generator, for instance. The purpose is to check that the power dip is not deep and long enough to affect the process. For instance, to see the large process pumps stop. Another important calculation is required for commissioning. It is the protection coordination study. The protection coordination study defines the settings of protections in order to ensure selectivity. Selectivity means that the protection of individual consumers will operate first before any higher level protection. For instance, if there is a short circuit in a particular pump, the protection of that pump only will operate, and not the protection of the higher level of the electrical distribution system. Therefore, the power supply will be cut only for this particular pump and not for other consumers. This synoptic summarizes the work of the electrical engineer. It starts with the inventory of all electrical power consumers and the calculation of the overall plant power demand. Then the electrical power distribution system is designed and the distribution equipment is specified. Once the equipment has been ordered and vendor drawings have been received, all installation and wiring diagrams can be issued. This concludes this presentation of the work and deliverables of the electrical discipline. Thank you for your attention.